Welcome to lesson 3.4. Last time we looked at the extreme value theorem, or EVT. This time we're going to be looking at the mean value theorem, also known as the MVT, and a special case of the mean value theorem known as Rolle's theorem. And we'll see how we can apply this theorem to help us describe the behavior of a function over a given interval. So in the first couple of examples, we're going to be exploring some graphs, and so we have actually 4 of them. Here are the first 2, f of x and g of x. Here is h of x and k of x. And what we're going to do is answer a series of questions for all 4 of these functions. So the first thing that we're asked to do is to draw the secant lines for each figure on the given interval. So if you remember, a secant line crosses the function at 2 points, whereas a tangent line touches it at only 1 point. Alright, so they have indicated for me the 2 points through which I should draw my secant line. So this gives us our secant line. Now in question 2, they also want me to draw a tangent line for each figure if possible, parallel to the secant line, and also between the endpoints of the given interval. Alright, well let me go ahead, and before I move on to the other figures, let me do that. And since they want it to be parallel, I am going to copy this line and shift it. And here is another one that we can bring down. Let me move my ruler out of the way, and let's see if we can identify the points where these tangent lines occur. And so this one seems to be right at x equals 7, and this one seems to be right at x equals 2.5. Now let's go ahead and sketch the secant line for figure 2. And so start with our first point. We'll do this one in orange so we don't get it mixed up with the other function. Alright? Now for h of x, we have a function that is not continuous. So let's just see what we can do here in terms of secant lines. So there is a secant line, and so we can also draw a parallel secant tangent line. So let's do that. Now my tangent line looks to be tangent at x equals 6. Now we should have another point for our interval located at 9, 4, and that's missing from my figure, so I'm going to draw that in, and also at 1, 6. So we'll put those 2 points in, and let's sketch a secant line through those 2. And so we can sketch our secant line through these 2 points, and then keeping our straight edge parallel, let's sketch a tangent line and see where it's located. So here we have our tangent line. Now this point of tangency appears to be located at about x equals 2.5. So let's put a point there, and we'll label that x equals 2.5. Alright, so in our first figure we've sketched secant lines, and we have located the values of c for which the tangent lines occur. In figure 2, we're not able to sketch a tangent line because I do not have a point on the curve that is differentiable and parallel to my secant line. In figure 3, we've sketched our secant lines with parallel tangent lines, and we've also identified our points C for each of our tangent lines. And let's take a look at figure 4 now. So the 2 indicated points for my interval are located at 1, 7 and at 5, 2. Let me sketch those secant lines, or that secant line. So here is our secant line passing through those 2 points. And keeping it parallel, let's see if we can sketch a tangent line. So identifying our point of tangency, the best candidate seems to be x equals 4. Alright, so let me close my ruler. And let's take a look at those questions again. So we've drawn our secant lines. We have drawn our tangent lines when possible. We have estimated the value of x equals c where this occurs. Explain why it's not possible. So let's take a look. So for figure 1, we had x equals 2.5 and x equals 7. In figure 2, we were not able to sketch a tangent line because we did not have a differentiable point that was parallel to our secant line. So that was not possible. In figure 3, we again had x equals 2.5 and then x equals 6. And then finally in example 4, we had x equals 4. So if you think back, one of the criteria that we considered for lots of things, but most recently the extreme value theorem, is the continuity of the function on the interval. So a good question for us to ask is, which of these functions are continuous on the given intervals? Well, let's take a look. 1 is continuous on the interval. 2 is also continuous on the interval. 3 was not. We had a discontinuity at x equals 5, but 4 was. So 1, 2, and 4. Now number 5 says, which functions are differentiable on the given intervals, which are not differentiable, if any, and why? So going back and looking, so 1 was continuous and differentiable everywhere on the interval. 2 was continuous but not differentiable. 3 was not continuous on the interval and therefore not differentiable. And 4 was continuous on the interval and differentiable on the interval. So this leaves us with 1 and 4. So now they tell us to take a look at h of x, and they want us to change the interval from 1 to 5, and they want to know if we can find an x equals c that will satisfy the mean value theorem. Let's take a look. So here we have our function h of x, and changing our interval from 1 to 5. Let me change colors to red, and let's put an endpoint. Well, we already have an endpoint at 5. All right, so let's do this. Let me sketch the secant line. And in this case, we seem to have a tangent line located at x equals 3.